Okay, let's double check that we're recording. Yes, okay. It's going to be respiration 3. Okay, and this continues alveolar ventilation, measurement of ventilation. This is respiratory volumes and capacities. I'm not going to talk really that much about these things. This is on top of page 934 because we are going to have a whole lab on these respiratory capacities and volumes. Next week's lab is going to be respiratory anatomy and then spirometry. And it turns out we're not actually going to measure these volumes because we have to take our mask off to do that, and we can't do that. So we're going to talk about what we normally do. And I've already mentioned one tidal volume, and that is one normal, restful, quiet inhalation. And exhalation is called tidal volume. All right. Variations of respiratory rhythm. Eupnea is normal respiration. Hyperventilation is very rapid ventilation, very rapid breathing. Hyperventilation. Hypoventilation is slower ventilation. And hyperpnea, or deeper ventilation. Okay, so we talk about gas exchange and transport now. We're going to talk about how the gas exchange occurs, what things affect this gas exchange, and how we transport these gases in the blood back and forth between the tissues and the lungs. So now we've talked about a third dead guy's law, Dalton's law, and talk about the composition of air. So what's in the air you're breathing right now? Well, most of it, if you think of oxygen being the most important component, but most of it's nitrogen. 78% or something of the air you're breathing is nitrogen. 21% is oxygen, and 0.04%, as I mentioned last time, is carbon dioxide. But when we talk about the amount of air of these different gases in the mixture that we're breathing, we're talking about what is called partial pressure. The partial pressure of oxygen, the partial pressure of CO2, and the partial pressure of nitrogen. And the way to get that is if the whole atmospheric pressure is 760 millimeters of mercury. And that's what the unit for all these partial pressures is, millimeters of mercury. So how many millimeters of mercury is oxygen? I should have done this math before we started. Take the percent, 21%, 0.21 times 760, and you'll get the partial pressure of oxygen in the environment. Multiply 0.78 times 760, you get the partial pressure of nitrogen, and so on and so forth. So we talk about this mixture of gases we're breathing in terms of partial pressure. And that's what Dalton's law says. A mixture of gases is a combination of all the partial pressures of all the gases in the mixture. Okay. And it's different out here than it is going to be in the alveoli. And that's because, remember, when we breathe in, we mix the fresh air with the dead space air that has a lower oxygen partial pressure and a much higher CO2 partial pressure. So here are the partial pressures. Okay, so all that's, actually I could just kind of look down here rather than do the math. 935, on top of page 935, we've already done the math. 760 millimeters of mercury times 20.9%. So the partial pressure of the air you're breathing right now is 159 millimeters of mercury. It's a little bit less than that because, as I said, you're a little bit above sea level, so it's a little less than 760. Remember, the higher you go, the lower the overall atmospheric pressure. 760 millimeters of mercury is called 1 atmosphere. And we're pretty close to that. Okay. I think this is on the next page. Yeah, page 936. Now look at this. Now I put the inspired air on the left. And this is not actually part of the figure, so I added it. Inspired air, PO2, 159 millimeters of mercury. I didn't put millimeters of mercury in there, but remember, that's the units for all of these. The PCO2 is 0.3 millimeters of mercury. Okay, what is it? When you get to the alveoli, what's the PO2? 104 millimeters of mercury. What's the PCO2? 40 millimeters of mercury in the alveolus. And again, why is that? Because the fresh air mixed with the dead space air. So we drop from 159 out here to 104 in the alveolus. And from 0.3 out here to 40 in the alveolus. Okay. What's the PO2 and PCO2 of the blood coming to the lungs in the pulmonary capillaries? PO2, 40 millimeters of mercury. PCO2, 45 millimeters of mercury. So what's going to happen? Oxygen is going to flow from the alveolus into the capillary because we got 104 over here and 40 over here. Then PCO2 is going to go in the opposite direction. The PCO2 is 45 in the pulmonary capillary, it's 40 in alveolus, CO2 is going to go in the other direction. And look at the PO2 and PCO2 of the blood leaving the alveolus in the pulmonary capillary that's leaving the alveolus. PO2, 104 millimeters of mercury, PCO2, 40 millimeters of mercury. So in other words, the partial pressure of these two gases in the capillaries has gone to equilibrium. That is, it's leaving at exactly the same level as the air in the alveolus. And this happens in 0.2 of a second. That blood is in contact with the alveolus for 0.2 of a second. And it goes to equilibrium. Okay. So then down below. So, but down below, when we get to the systemic circulation, we look at the PO2 in the systemic capillary coming in. The PO2 is 95 millimeters of mercury, and the PCO2 is 40 millimeters of mercury. Well, wait a minute, what happened here? We lost some in the PO2. We lost like 9 millimeters of mercury. Why? Where did the oxygen go? Well, here's the thing. The pulmonary capillaries leaving the alveolus will come in, and that's going to be a venule, a pulmonary vein. It's going to be come into contact with a bronchial vein. The bronchial vein has just supplied oxygen to all the cells in the conducting pathways. So it's deoxygenated blood. So what's going to happen is a little bit of deoxygenated blood from the bronchial veins is going to mix with oxygenated blood from the pulmonary veins. And so the blood going back to the heart actually has a little lower PO2 than the blood in the pulmonary capillaries leaving the alveolus. But still, it's higher than the PO2 in the systemic tissues, which is 40 millimeters of mercury. So oxygen can come out of the blood into the interstitial fluid, into the cells of the systemic tissues. And the PCO2, the systemic tissues, 45 millimeters of mercury, higher than it is in the blood. So CO2 comes into the blood. And then look at the at the partial pressure of these two gases in the capillaries leaving the systemic tissues, it's gone to equilibrium again. PO2 40 milliliters of mercury, PCO2 45. The same as it is back when we get into the pulmonary capillaries, bring in CO2 back to the lungs. And we do this over and over again. And then look at this expired air. The air that you're expiring still has 116 millimeters of mercury in it. PCO2 is 32 millimeters, a lot higher. So we're going to see, we're going to use that when we do the group activity. We need those numbers when we do the group activity to talk about why CPR works. Okay. Okay. I think this is the last dead guy's law, Henry's law, the law of solubility. How much oxygen is dissolved in liquid that's in contact with a gas mixture? So amount dissolved in an aqueous solution. So you have this aqueous solution, and you have this air mixture on top. How much gas is dissolved in that liquid is determined by the partial pressure differences across the air versus the water. The higher the partial pressure in this air, the greater the amount of oxygen in this liquid. The greater amount of CO2 in this air, the greater amount in the liquid. But it also depends upon what's called the solubility efficient of the gas. And I'm not going to get into these numbers, but all that the solubility coefficient means is how soluble is this gas in this liquid? All right. And it just turns out that oxygen is actually not all that soluble in water. CO2 is very soluble in water. So we're going to see that how these work in alveolar gas exchange to determine how much oxygen leaves alveoli, how much CO2 comes into alveoli. It has to, as I said, it has to do with the partial pressure difference between the alveoli and the capillary, and how soluble these gases are in liquid. Because remember, in the alveolus, it's a gas. In the blood, it's liquid. So we got a gas-liquid interface there. All right. Okay, variables affecting gas exchange. So how fast does gas diffuse, really? What things affect the speed of diffusion? This is very important, as I mentioned, because your blood only has 0.2 of a second to get saturated with oxygen and to get rid of a fair amount of CO2. So the pressure gradient of the gases, the higher the pressure gradient across the respiratory membrane, the more gas is going to flow. The solubility of gases. How soluble are the gases in aqueous solution? The more soluble they are, the more it's going to pass. The less soluble they are, the less it's going to pass. The membrane thickness. How thick the membrane is. And usually under normal circumstances, it's very, very thin. And remember, diffusion is very rapid for very tiny distances. But even greater distances, even slightly greater differences, the rate of diffusion falls really off. This is the danger of pulmonary edema. If fluid builds up in your lungs, it pushes your type 1 alveolar cells away from the endothelial cells, and the respiratory membrane gets thicker and thicker. And that really slows down and decreases the rate of diffusion. Membrane area. How much area we got how much surface area is there for this gas exchange to occur. And it's a huge surface area. As I mentioned before, you got about the surface area of a tennis court in all the alveoli in all of your lungs. And this is one as in a certain pathological condition called emphysema. The alveoli break down and you have fewer alveoli and larger alveoli, much less surface area. This decreases the amount of gas that can be exchanged. And then there's ventilation perfusion coupling. This is, so ventilation is bringing air into your lungs. Perfusion is bringing blood to your lungs. So what you want to do is bring blood to where the air is. And because here's the thing, when you're doing regular, normal, quiet breathing, tidal volume breathing, do you fill up your whole lungs with air? Well, no, you don't. You'd have to breathe as much as you can to fill up your lungs completely with air. So you're only filling up part of your lungs with air. Well, where do you want to put the blood that comes to your lungs? Do you want to bring the blood to alveoli that are not being ventilated? No, you want to bring the blood to the ones that are being ventilated. So this is called ventilation perfusion coupling. And so here's the thing about those precapillary sphincters, that what opens and closes precapillary sphincters. In the chapter on blood vessels, we learned that those in almost all tissues in your body, low oxygen will open precapillary sphincters, high oxygen will close them, except in the lungs, where it's reversed. High oxygen will open capillaries, low oxygen will close. This is the way blood is shunted to the areas of the lung that are being ventilated, that have the high oxygen. And this is called ventilation perfusion coupling. Okay, now getting into gas transport. How is this gas transported in your blood? I'm going to talk about the hemoglobin dissociation curve. I'm going to show you that in a moment. You're going to have to be able to read that. And what it means is, so we know that oxygen is carried by hemoglobin. And each hemoglobin is 4 polypeptide chains. Each chain carries one oxygen molecule, O2 molecule, associated with the iron in what's called the heme group. All right. And this is where 98% of the oxygen carried in your blood is carried in erythrocytes attached to hemoglobin. Like 2% is just oxygen dissolved in the blood plasma. Because remember, oxygen is not that soluble in water. So there's very little oxygen, relatively, dissolved in the plasma. It's almost all in red blood cells, erythrocytes in the hemoglobin in erythrocytes. And we're going to talk about oxygen reserve in a moment, and utilization coefficient. Because remember, your hemoglobin is essentially saturated with oxygen when it leaves your lungs. And this is in a normal, healthy person. The oxygen leaving your lungs is, the hemoglobin is 100% saturated. This means every hemoglobin is carrying 4 oxygen molecules. When it gets down and unloads oxygen in the systemic tissues, it really only unloads 25% of the oxygen it's carried. The hemoglobin that's leaving, a normally respiring tissue is still 75% oxygen. So like every hemoglobin is carrying like 3 oxygen molecules when it goes back to the lungs. It just picks up that 25% in the lungs. But if you have your tissue that's really moving fast and metabolizing quickly, like really exercising muscle, more oxygen is going to be released by the hemoglobin, because one of the major things that determines how much oxygen is released by hemoglobin is what is the partial pressure of oxygen that the hemoglobin is presented with. This is called the oxygen reserve. So that if you have really metabolizing tissue, you can dump out more oxygen to the tissues that need it more than other ones that don't need it more. What was I going to say? So we'll look at so oxygen, how strongly oxygen is attached to hemoglobin is a variable thing. Hemoglobin is a really sophisticated molecule. It carries oxygen, but how tightly does it carry oxygen? Because it has to carry oxygen, right, and hold on to it. Then it has to release it when it needs to. So the strength of that bond is a variable thing. You want it to be really strong in the lungs to pick up the oxygen. And you want it to be weaker in the systemic tissues where you want it to get rid of oxygen, when you want to dump oxygen. Okay. Carbon dioxide. A little more complicated how carbon dioxide is carried in the blood. Most of it's carried as bicarbonate, 70%. And oh, wait a minute, I think I'm going to have to modify this PowerPoint. I'm not sure I've got the equation that shows you how CO2 is carried as bicarbonate. So let's hold off on that. We'll just look at it right now. It's carried in an ion called bicarbonate. It's HCO3 minus. It's called bicarbonate. 23% is actually bound to hemoglobin. So you gotta remember that hemoglobin binds oxygen. It also binds carbon dioxide. It does is called carbamino hemoglobin. And then 7% is actually dissolved in plasma. So CO2 is much more soluble in an aqueous solution than oxygen is, and so 7%. So there's 3 ways that carbon dioxide is carried in the blood. Here is the oxygen dissociation curve. And you're going to have to know how to read this. If I put this on the exam, you're going to need to know how to read it. And so what it is percent oxygen saturation of hemoglobin as a function of PO2, the partial pressure of oxygen that it's exposed to. So up at the very top is at E is where is in the lungs, where you have the hemoglobin exposed to 104 partial pressure of 104 millimeters of mercury, and the hemoglobin gets essentially saturated, 100% saturated. Now remember what the PO2 was in the systemic tissues. It was 40 millimeters of mercury. We'll go down to 40 on the x-axis, go down to 40, you go up and hit that line at B, you go across, what do you get? 75%. So this is what I was saying. Hemoglobin is going to get rid of 25% of the oxygen it's carrying and give it to the systemic tissues. And then when it goes back to the lungs, still 75% saturated. But what if this is muscle that's really using a lot of oxygen, and the oxygen partial pressure really drops in muscle that's really being active? Let's say it drops down to 20 from 40. It's half of what it was. We'll then go over to 20 on the x-axis, go up to where it says A, go across. What's the percent saturation of hemoglobin? 35%. So it's dropped from 75 to 35, 40 millimeters of mercury. So this is what we're talking about, the oxygen reserve. So we can dump more oxygen to tissues if this tissue is really being active and really needs more oxygen. And then it goes back to the lungs at 35% saturated rather than 75%. But even in 0.2 of a second it spends in the lungs, it still gets to be 100% saturated when it leaves. Doesn't matter if it's 35, 75, whatever. When it leaves, it's 100% saturated. Okay. Carbon dioxide loading in systemic gas exchange. All right, so carbon dioxide is coming out of the interstitial fluid, the cells that in the systemic tissue, and it's binding with hydrogen ion to, okay, so I'm gonna have to break it right here, make this a short one, because I really need to give you this equation about how, what bicarbonate is, and actually how bicarbonate, the partial pressure of bicarbonate in your blood is linked to pH. And that has to do with this chloride shift in this whole thing. So I need to, I'm going to break it here. This will be a short one, and come back and make a slide of the actual equation that I'm talking about. I could do it on a board here, but I think it's too small. So let me break here, be back a little bit, and with a slide showing that equation. So I'll be back in a moment. Okay, we're back. Here is a slide just made. This is I call this the ubiquitous equation because you're going to see it over and over and over again in subsequent chapters. You can see it in the digestive chapter, in the renal chapter, in electrolytes, fluids and electrolytes. This is how CO2 is related to pH, and also how CO2, the major way CO2 is carried in the blood. To the left, H2O. Now I can't make superscripts and subscripts here. So it's H2O plus CO2, you know what those are, water and carbon dioxide, form what's called carbonic acid, H2CO3. This spontaneously breaks down, I think it's by an enzyme called carbonic anhydrase, that's like in all cells, to hydrogen ion plus HCO3 minus, which is bicarbonate ion. So notice H plus on the right-hand side. So, and the direction in which this equation flows depends upon how much of the reactants are there compared to the products. Is there lots of water and CO2 compared to carbonic acid? Then lots of carbonic acid will be made. If lots of carbonic acid is made, lots will break down into hydrogen ion and bicarbonate. So if you have a lot of CO2 in your blood, you will have a lot of hydrogen ion in your blood. And that will make your blood more acidic. If there's a lot more hydrogen ion and bicarbonate in the blood than carbonic acid, this is a reversible reaction. I should have made reversible errors here, but I couldn't. They are reversible errors. Then hydrogen ion and bicarbonate will combine to form carbonic acid. Carbonic acid will break down into H2O and CO2, and the amount of hydrogen ion in the blood will decrease, and your blood pH will go up. This equation is why you're breathing 12 times per minute, to make sure you get rid of enough CO2, but not too much, to keep your blood at 7.4, pH of 7.4. And if I wanted to, I could voluntarily screw up my blood pH. If I start hyperventilating, what's that going to do? It's going to shift that equation to the left because you've blown off too much CO2. So it's like a teeter-totter. Here's H2O and CO2, you've decreased this. The teeter-totter goes like this, the equation flows in this direction, the hydrogen ion goes down, that's called respiratory alkalosis. So when I hold my breath, my blood will eventually become more and more and more acidic because now the teeter-totter is in the other way. CO2 is rising if you're not blowing it off, right? Push the equation to the right. This will cause more hydrogen ion to be produced. Your blood becomes more acidic. That's called respiratory acidosis. And we'll talk a lot more about that in the fluids and electrolytes chapter when we discuss more thoroughly the regulation of blood pH. Very important equation to learn. It's best to memorize this equation. You can see it over and over again. Okay. So now, wait a minute here. Oh, I forgot to make it slideshow. Hang on a second. Right there. So now we can understand this chloride shift in it. Oh, wait, let me go back. This chloride shift. So as oxygen, as CO2 comes out of the tissues into the blood and into the red blood cell, what happens is it combines with water to form more carbonic acid, which forms more hydrogen ion and bicarbonate. The bicarbonate leaves the red blood cell and goes into the blood. Well, this is negative ion leaving the red blood cell. So to maintain the membrane potential, a negative ion has to come into the red blood cell, and that's called the chloride shift. Now, in the alveolar gas exchange, it's exactly opposite. Remember, the CO2 now combines with water to form, the bicarbonate now goes from the plasma into the red blood cell, combines with the hydrogen ions in the red blood cell to form more carbonic acid. This breaks up into more water and CO2. The CO2 leaves the red blood cell and goes into the alveolus. But again, this is bringing negative charge into red blood cells. So now we have to get rid of negative charge. So we get rid of chloride ion. This is called the reverse chloride shift. And this is all shown in this one right here. And it looks kind of busy, but and this is conversion of CO2 to CO2 in systemic capillaries on top, and then in reverse in alveolar capillaries. Notice the CO2 comes in, binds with water. There's that equation right there. The bicarbonate leaves. Remember, 70% of CO2 is carried in plasma as bicarbonate by this process here, and the chloride has to come in. And then in the lungs, exact opposite. The bicarbonate comes back into the red blood cell. More CO2 is produced. Leaves, goes into the plasma, into the alveolus, and we dump CO2. Okay. Okay. Affinity of hemoglobin for O2 is variable. There are things that affect how the strength of the bond between oxygen and hemoglobin. It says compare with fetal hemoglobin. This is interesting. At one time you had fetal hemoglobin. Now, do you think a fetus hemoglobin would have greater or less affinity for oxygen, or the same affinity, as adult hemoglobin. Well, think about it. The fetus has to take oxygen away from mom's hemoglobin, right? So that's what it has to do. So it has to have a greater affinity for oxygen, a stronger bond to oxygen than adult hemoglobin. Otherwise, the fetus would need to pull hemoglobin oxygen off of mom's hemoglobin. Then when you're born, you switch over to adult hemoglobin. Okay, what kind of things affect the affinity of hemoglobin or oxygen? Ambient O2 levels. And we saw this in the hemoglobin dissociation curve. What's the local PO2? The lower it is, the more oxygen comes off of hemoglobin, the less affinity hemoglobin has for oxygen. It's the weaker the bond. Okay. Temperature has an effect. The higher the temperature, the weaker the bond of oxygen and hemoglobin. Does that make sense now for dumping oxygen in tissues? Well, yeah. What happens to your muscles when you exercise? Do they get hot? They get a lot hotter. And this helps dump oxygen off of hemoglobin. Because the hotter it is, the lower the affinity that hemoglobin has for oxygen, the weaker the bond. All right. What else? The Bohr effect, pH. Lower the pH, the lower the affinity of oxygen for hemoglobin. Does this make sense? Well, yeah. When you have tissue that's metabolizing very rapidly, it makes lots of acids, just as metabolic byproducts. And the more acid it is, the lower the bond affinity between oxygen and hemoglobin, the more oxygen comes off. That's called the Bohr effect. This level BPG. This is almost the same as the Bohr effect, in the fact that BPG, I forget what it refers to, is a metabolic intermediate that really metabolizes in tissues that make a lot of. And so if there's a lot of it in the area, it reduces the bond between hemoglobin and oxygen, and more oxygen comes off. Okay. Then the Haldane effect. Binding of carbon dioxide. Remember, carbon dioxide also binds to hemoglobin. It's one of the ways 23% of carbon dioxide carried in blood is carried bound to hemoglobin. With the more carbon dioxide that binds to hemoglobin, the less oxygen can bind. Right? So in the tissues, there's lots of CO2. It's coming in, it's binding to hemoglobin, reducing the bond between hemoglobin and oxygen, more oxygen comes off. So you see, in all those conditions, they're exact opposite in the lungs. Temperature is lower, the pH is higher, there's not very much pH. The temperature is a little bit lower, and all those help to bring up, to increase the affinity of oxygen hemoglobin and to load oxygen onto hemoglobin. And here they all are right here. And this is a copy of page 943, with all the things that affect the hemoglobin and oxygen release. And I'm not going to go over them again. You can see that the hemoglobin dissociation curves, how they can shift from to the left or to the right, depending upon the temperature. Shift to the left means a greater affinity, a lower temperature. Shift to the right is a less affinity at a higher temperature. Same thing with pH. A higher pH shifts the curve to the left, increases the affinity. A lower pH shifts it to the right, decreases the affinity. Okay, hyper and hypoventilation. Hyperventilation is breathing too rapidly. Hypoventilation is breathing too slowly. And you sometimes jump right into hyperventilation due to fear, anxiety. What's called hyperventilation, and this will come from the amygdala, also bypassing the respiratory control center and make you hyperventilate if you get anxious or afraid. Okay, so what will hyperventilation do? We get extra oxygen for hyperventilation? No, you won't, because if you're breathing normally or more rapidly, your blood is 100% oxygen when it leaves the lungs, and breathing more rapidly is not going to do anything. But what it'll do is you'll lose more carbon dioxide. This is called a hypocapnia. And I demonstrated it before. I voluntarily hyperventilated and started feeling a little woozy because I was losing too much CO2 and my blood pH was rising. It also causes a little vasoconstriction, brain arterioles in hyperventilation. It causes respiratory alkalosis, as I just mentioned. That means the pH of my blood actually rose. Okay, hypoventilation, that could be due to injury, maybe obesity, pressure against the lungs. So that's and bradyapnea is breathing too slowly. Hypopnea is breathing too shallow. That's both kinds of hypoventilation. Can cause both hypoxia and hypercapnia. So here, hypoxia is your blood not carrying enough oxygen. So hyperventilating doesn't change oxygen, but hypoventilation can. It can decrease the amount of oxygen that your blood is picking up, and so your blood, your hemoglobin isn't 100% saturated when it leaves the lungs. And then what it also causes hypercapnia. This is the opposite of hypocapnia. Hypercapnia is too much CO2 in your blood because you're not breathing deeply enough or often enough to get rid of the CO2 you should be getting rid of to keep your blood pH constant. So hypercapnia will cause respiratory acidosis. Too much CO2 in your blood, and this will lower your blood pH. Okay, let me break it there, and I don't want to make sure this thing isn't too long, so let me break it here, and then we'll come back and do I think this respiration 3. We'll come back and do respiration 4. I'll see you in a little bit.